Okay, so I want to talk about short-run production and costs. I'm going to start by just reviewing a little bit from the production notes, which is something I talked about briefly before spring break. This idea of short-run production. And the idea there was that some inputs are more flexible than others. And this is actually, and so just the example here is that often it's easier for firms to reduce labor hours than they can, say, reduce capital. So unfortunately, this is quite timely at the moment because we see that for the most part, if you go downtown and you look at, say, bars and restaurants, wherever you are in the world, but for the most part, these firms have reduced labor hours pretty significantly, but they still, they signed a lease, and so they still have to pay for all of the capital that they're using. So there was an article in news recently about Cheesecake Factory saying that it's not going to pay its lease, but that seems to be more the exception than the rule. And the reason that's news is because they're breaking a contract because they don't want to pay for their capital, but they're already pretty easily reducing labor, and that has been sort of less newsworthy. So anyway, the idea here. Right, and this doesn't just happen during pandemics, this happens often, right? So I think, before spring break, I talked about how it's spring break in Athens, right? A lot of times bars will not open their doors because they don't want to pay their workers because there's very little demand, right? But they are still, renting the space and paying for that. So this is, we often just want to think about, what is the distinction between short run and long run, because firms are adjusting labor input, can adjust their labor inputs more easily. So I use the term here short run, and the short run, just to be somewhat technical about this, is just a period of time in which quantities of one or more inputs cannot be adjusted. All right, and so in this case, like if a firm has signed a year-long lease, that means that the short run would be, say, a year for that firm, right? Because they can't adjust their capital input or their lease for another year. And we're going to call those inputs that cannot be adjusted fixed inputs. And in sort of in the model that we're going to be using in class, this is typically going to be capital. All right, so we're going to allow labor to adjust, and capital will be fixed for the models that we're going to be working on. Okay, so now I want to transition to so this was just sort of the review of production functions. Now I want to transition to talking about short-run costs. And if you want to follow along in the notes, that's going to be page 9 of the cost minimization notes. That's with solutions. So the idea and the thing that we've been doing in the cost minimization lecture is we want to find, what is the cheapest combination of capital and labor for a firm to produce, right? And that's what we call a cost function. So the goal here, right, is to find the firm's cost function, or in this case, the short run cost function. Okay, and let's just recall, right, that a cost function, when I say those words, cost function, I mean something very specific. I mean the cost function is the cheapest way for firms to produce Q units of output. All right, so firms are trying to decide how much capital and labor to use, right, to produce Q units of output, and they're trying to find, what is the cheapest way to do that? What is the cheapest combination of capital and labor, right, to do that? All right. And that's what a cost function tells us. So, and in this situation, right, how does a firm, the question that we're trying to get at, right, our goal is to find the short run cost function. So really what we're trying to do is figure out how to minimize the firm's costs. For a given amount of quantity. All right. But remember, the firm can't influence capital. Capital is fixed. So they can only choose how much labor they want to adjust. Okay, and that's the key point of basically the short run problem. They can only adjust labor. What does that mean? Right? That means that all they have to do is all you have to do is find the minimum amount of labor that they need in order to produce Q units of output. All right, and so actually it turns out that if all you're trying to do is find the minimum amount of labor necessary, this is actually a very easy problem because you only have one thing you're adjusting, and it's only going to be turning into just find this amount of labor, right? So as we'll see, this is a very easy problem if you can just remember how to do the short run cost function, and that this is sort of the distinction of the short run cost function. Your life will be very easy, and you'll be very happy if this is the one that I give you on the exam. So let me write down the recipe to show you how to solve this problem. So what we need to do, right, or basically what I said, right, what we need to do is find the minimum amount of labor to produce Q units of output. So this implies the following recipe. So first, let's just write down the cost function, or sorry, the production function. All right, and then we're just going to solve for L. And then finally, we're going to write down, basically write this into the cost function. All right, and again, this is a straightforward problem. Like, you should be pretty happy if you see this on an exam. These are not too bad, so don't be intimidated. Okay, so let me give an example. So the example that I have in the notes is production function Q is L to the 1/2, K to the 1/2. All right, K naught, or the original amount of capital, is 25. The wage rate is 9. The rental rate is 4. And quantity is equal to 100. All right, so the firm's goal is to produce 100 units of output, or in this case, and we just want to find what are the firm's short-run costs. All right, I'm not saying the short-run cost function here because I'm giving you Q. All right, we'll do that later where we leave Q as a variable, because that's when we're going to have a cost function, right? Something as a function of Q, but just to make things easier, I'm going to give you that Q is 100, and then we'll do that one next, or that will be a handout, I guess. So what do we have to do? Well, let's just follow our recipe. So first, step 1. All right, we're going to write down the production function. All right, and so in this case, that's going to be Q is equal to L to the 1/2, K to the 1/2, right? That's what we were given here. Okay. And then we're just going to plug in Q naught and, Q and K naught. So that's going to be 100, because that's what I said Q was, right, is equal to L to the 1/2, 25 to the 1/2. Right, and then step 2, right, we're just going to solve for L. So this case, 100 is equal to square root of L, right, times square root of 25, which is 5. So L to the 1/2 is equal to 100 over 5, or L is equal to 20 squared, okay, or L is equal to 400. Okay. So that's step 2, solve for L. Step 3, we're just going to write down the cost function and plug in the values we have. So in this case, we're writing C is equal to W times LC plus R times K naught. So for the long run problems, right, what we did is W times LC plus R times KC, right, the cheapest combination of capital and labor. Right, for this one, we can't change capital, so capital is fixed at K naught, and so the firm is just choosing the cheapest amount of labor. In this case, using the numbers that we've been given, this is going to be 9 times 400 plus 4 times 25, 4 and 25, which is equal to 3,700. Okay. What does this tell us? Right, so this tells us the cheapest way to produce 100 units of output. All right. So again, this is not a cost function, right? Because this isn't a costs are not a function of Q, right? This is just telling us the cheapest way if we wanted to produce 100 units of output. Now, if we want an actual cost function, which we're going to be working out with later when we say maximize profit, we're going to want to leave Q as a variable, which is what we're going to do in the handout. So I'm going to stop this video here, but if you're sort of following along, next thing to do is try handout H07 SR cost function. And presumably the one without solutions. I will post a video of the solutions and a hard copy of the solutions for you to follow along. All right, so I'm going to keep going with the short run cost lecture. So this video is just a couple of definitions, basically starting on page 10. The first definition here is a fixed cost, which is a cost that does not change with the level of output. And typically in our models, fixed cost is going to be like capital, or the cost associated with capital in our models. Which is the rental rate times the amount of fixed capital that the firm has. Right, so again, in the short run, firms have capital. We normally think of capital as being the fixed input. So this might be, the lease that, a company has that they can't break. And then the cost associated with that is just the cost of having that capital, right? The rental rate times the amount of capital that they have. So there's fixed costs and then also variable costs, which are just costs that change in the level of output. It's really that simple. And again, variable costs are, which we're going to denote with a VC, is a function of Q, and it's a function of Q because it changes in the amount of output. All right, and variable costs, we're typically going to think of them as being the wage bill. So in our model, this is the wage bill, which is just W times L, right? The wage rate times the amount of labor, right? The idea being, if Little Italy wanted to say produce more output, right? The thing that they would probably do is hire more workers, right? They can't very quickly get a larger store or say rent more stoves. Right, but they can add more workers or more hours very quickly. And so these are sort of the costs that we think that in the short run vary for the firm. And then finally, there will be total cost, which is just the sum of the two. And I'm going to write total cost in two different ways. I'll either say total cost TC of Q, or as just C of Q. This is just, I guess, at this point in the lecture, I sort of like to have TC just to make it clear that we're talking about total costs. But so far in the lectures, up to this point, we've been just using C. But these are going to be pretty interchangeable throughout, though often we'll use TC. We might think of this as being in the short run, though that's not sort of going to hold throughout. That's not perfectly general. So in the last, in the video for the handout, we solved for total cost. And we got total cost is equal to W times LC plus R times K naught. So this is always going to be the case with cost, where it's the labor times, or the wage rate times the cheapest way to make that amount of input, right, times the rental rate times the amount of capital. This first term, right, when we solved out for it, was W times Q squared over K naught, right? And then this was still just R times K naught, right? And so this, right, is a function of Q, right? And so this whole thing is a function of Q, but this is the variable cost, right? Because it is the part that depends on Q only. Right, and then this part here is the fixed cost. Okay, so I'm going to skip ahead now to page 14 in the notes. In the middle of page 14, I give basically a running example of a cost function that might exist. There's nothing really special about these numbers. I just wanted something that graphs kind of nicely, as we'll see in a couple minutes. This just has lines that are nice to work with. But that's really all that's important about this particular cost function. So the cost function, Q cubed minus 8Q squared plus 25Q plus 20. So the first question here, which part of this is variable cost and which part of this is fixed cost? Right, so the plus 20 part is the fixed cost because it doesn't depend on Q, right? The firm could produce 30 units of output, or they could produce no units of output, or they could produce 100 units of output. Regardless, right, whatever Q I plug in, this firm is going to have to pay this $20, okay? The remainder of this, right, all depends on Q, so this is all going to fall under variable costs. Right, it depends on Q. All right, so I have three definitions of different types of, I guess, average or variable costs, or average cost. So the first is average total cost, which is a function of Q. Which is just the total cost divided by Q. Okay, so if costs are 100, but you produce 10 units, right? The average cost is 10. If costs are 200, but you produce 10 units, right? Then the average cost is 20. If the firm were to produce 300 units, the cost of producing 300 units. If the cost of producing 10 units is 300, the average total cost then is 30. So in this example, we're just going to divide this whole function here by Q. So average total cost is going to be Q cubed minus 8Q squared plus 25Q plus 20 all over Q. or q squared minus 8q plus 25 plus 20 over q. Okay. Average variable cost, it's the same idea, right? We're going to just divide variable cost by q. And so in this example, we're only going to take into account the variable cost, just this part of the function, and divide by q. So that's going to be q cubed plus or minus 8q squared plus 25q over q, which is q squared minus 8q plus 25. Right? And then finally, marginal cost. Which is just the derivative of total cost with respect to q. So in this case, we're just going to take the derivative of total cost with respect to q, and that's 3q squared minus 16q plus 25. Okay. One thing to note about marginal cost is that you can use either variable cost or total cost. Okay, it doesn't matter which one because fixed costs don't depend on q, and so when we take the derivative, it zeroes out. So just to derive that, so we have marginal cost is equal to the derivative of total cost with respect to q, right? But we can write total cost as average cost, right, plus fixed cost. And so we can rewrite this using the sum or difference rule as variable costs plus the derivative of fixed costs. And of course, the derivative of fixed costs is 0 because they don't depend on q. And so this is just the derivative of variable costs with respect to q. All right, so now I want to talk about the relationship between average variable cost, average total cost, and marginal cost, and how they're all shaped. So what I'm showing right now in this graph is the graph of the same function that we used that we've been using in our running example. The table at the top shows the actual values, right? So when q is equal to 1, if you were to plug that in, you should get a total cost of 38, and like as we said, the fixed cost should be 20, and the variable cost would be 18 if you were to plug 1 into this function. And then the graph below just graphs the values from this table. So the first thing that I want us to see is that at least with this function, average variable costs are rising. Right, and so the average variable cost function is this silver line given here, and so that's, as we see, rising over time. The reason that they might be rising, or we think they might be rising, is diminishing returns. Okay, so this is just at the moment like something that due to just this function that I've assumed. But in general, we think that average variable costs are rising at least when Q is large. And because of diminishing returns, for example, if there are too many cooks in the kitchen, right, it becomes harder for labor to be as efficient, and so average variable costs will rise. We generally think that average total cost may be more U-shaped, which we again see in this picture, just based on some arbitrary function. And there are two things going on here that make average total cost U-shaped. So when Q is small, fixed costs are high relative to variable costs. Okay, so fixed costs in this case are 20, right? Average fixed costs are when there's just one unit being produced, it's also 20, right? But as this goes to 0, the fixed cost gets spread across fewer and fewer units, and so the fixed costs rise, and so total costs are big, right? So if quantity is 0, right, average total cost is 0 over 20, right, which at least in the limit, right, goes to infinity. Average total costs get very big because average fixed costs are very high. And they're not being spread across a number of units. Right? When Q gets big, average total costs go up again, right? Because average variable costs are rising. Right? And what we should see, right, and we see in this graph, is that average variable costs and average variable costs and average total costs are going to converge. And the reason they do that is because average fixed costs go to nothing and average total costs is just average fixed cost plus average variable costs. So average variable cost and average total cost converge when Q gets large because fixed costs get spread over many units. Right? And then because average variable costs are rising, right, average total cost will also be rising, right, which is why we see U-shaped average total cost, this blue line. Right. The last point that I want to make is that marginal costs are going to cross both average total cost and average variable costs at their minimums. Right. So we see that graphically here. This yellow line is marginal cost. It crosses average variable cost here at its minimum. It crosses average total cost also at its minimum. Why does that happen? Well, the idea is that if the marginal unit, right, if the marginal unit, or in this case marginal cost, is say greater than, let's just say, average total cost, right, then average total costs are increasing. All right, and we can see that on the graph here, right? When the marginal costs are above average total costs are increasing, right? The opposite is also true. So if marginal costs are below average total cost, like in this part of the graph, right, then average total costs are decreasing. And this is intuitive. So the example that I like to give here, if you think about, and this sort of holds true for all kinds of functions, that the marginal is always and average always have this sort of relationship, right? The example that I often will give is your GPA. Right, so if you have like a 3.5 and you get an A, right, that brings up your GPA. But your marginal grade, right, that A is greater than your average, and so it increases the average. If you have a 3.5 and you get a B, right, that marginal grade is a 3, and so that's going to decrease the average because the marginal value is less than the average. All right, so this is just a quick note about comparing long run and short run costs. This is page 12 of the lecture notes. And really the point that I want to make here is that long run average costs are always below short run average costs. Okay, so let's talk intuitively about why that is, and then we'll talk a little bit about sort of what that means and sort of where we see this in practice. Well, first of all, why is that? Right? Why are long-run average costs always below short-run average costs? Well, the reason is that in the long run, firms can adjust both capital and labor. Right, so when you were doing the problems, the long run cost problems, these were what you were doing before break, right? We had to do all of this math because we need to figure out both the optimal level of capital and labor. Right? In the short run, right, firms only choose labor. And so they may be stuck with a suboptimal amount of capital. All right, so what is an example of this? Right? What is an example of a firm being stuck with a suboptimal amount of capital? Well, like think about any store right now, right? Or any restaurant, or Little Italy right now, right? They're all closed, right? And so their output, you know, except for maybe takeout orders, is basically zero, right? And so they aren't selling anything, right? In an ideal world, they would probably not want to pay rent, right? At the moment, all of these stores' costs are above their revenue and they're losing money, right? If we were in a long run world, which we're not, right, where like demand at all of these restaurants is zero, right, these firms would adjust both capital and labor, right, to be zero, right? And then they wouldn't have any costs and it wouldn't matter that they're not taking in any revenue. Right? But at the moment, they can't do that because they've signed leases. And so they're using way too much capital, right? Because they're spending lots of money on things that are not being used productively at the moment. All right, so that's why, sort of intuitively, why long run costs are always below short run costs. Just to be a little bit more sort of rigorous about this, right? The way that we know that this is true, right, is suppose, and this is sort of a by contradiction, right? Suppose that we found some combination of labor and capital, and that's going to be a fixed amount of capital, and let's call that L star and K star, right? Where short run costs are below average costs. Short run average costs are below long run average costs. Right? Can this exist? Right? And the answer here is no, right? Because in the long run, right, the firm could just choose this amount of labor and capital. Right? And so it can never be the case that short run average costs are below long run average costs, right? Because the firm can always be more efficient in the long run because it has the freedom to actually just choose that optimal amount of short run or something else if there's a more efficient combination of capital and labor. So the last part of this lecture I want to talk about is economies of scale. And a cost function is said to exhibit economies of scale. If producing more output is cheaper per unit. All right, so, and then diseconomies of scale is when it gets more expensive. Economies of scale are similar to returns to scale, except for economies of scale corresponds with cost functions, right, where returns to scale was related to production functions and how output increases with inputs. So one way to to see how whether or not a firm has economies of scale or a cost function has economies of scale is to see whether or not the average cost curve is increasing or decreasing, right? So if we look at just this example, right, for the first unit it cost $38, right? For the second unit the total cost was 46. So that second unit, or sorry, for the 2 units, the average cost was 23 rather than 38. Right, so at this point in the cost curve, right, the firm has economies of scale because the cost per unit is going down. Right, more output is cheaper per unit. Okay, we can also see this in the graph. Right, the blue line is the average total cost curve, and it's declining. Right, and then at some point, the average total cost curve rises, and the firm at that point is said to face diseconomies of scale. Okay. So how do we know if a firm has economies or diseconomies of scale? Right. Well, the way that we can figure this out, right, is we just want to know, is the average cost curve increasing or decreasing? So we're going to take the derivative of the average cost curve. right? Just recall that derivatives tell us about slopes, right? And so whether or not the slope is of the average cost curve is increasing or decreasing will tell us whether or not there are economies of scale. Recall, it needs to be the derivative of the average cost curve, right? Total costs are always increasing, right? Because as you add more, as you produce more output, it's just more expensive, right? But whether or not the average cost curve is decreasing is a more interesting question, or tells us about whether things are getting cheaper per unit. So the example that I have in my notes is a cost curve C of Q is equal to Q, 2 times Q to the 2 times the square root of Q, right? And what we want to do, right, or the question, right, does this function exhibit economies or diseconomies of scale? All right, so how do we figure this out? All right, well, first, right, find the average cost curve. Right, because that's what we want to take the derivative of. The average cost curve is just equal to CQ over Q, right? Or 2 times square root of Q, which is what we were given as costs, divided by Q, right? Okay, so this is like 2 times Q to the 1/2 over Q to the 1, right? We can subtract the exponents, right? And so this is 2 times Q to the 1/2 minus 1, or 2 times Q to the negative 1/2. All right, so that's the average cost curve. Now we just want to take the derivative of the average cost curve with respect to Q. So what we're going to do is we're going to take down the 1/2 and this the negative 1/2, and so there's going to be negative 1/2 times 2, right, times Q to the negative 3/2, right? And then we want to figure out, well, is this bigger or smaller than 0, right? Well, Q is always going to be positive, so this thing is always negative because this first part is negative. So this is less than 0. All right, what does that tell us, right? Economies or diseconomies of scale? So take a minute just to think about that, maybe pause the video for a second, right? So what this tells us is that average costs are falling, right? The average cost curve is declining because this is negative, right? So additional units are less expensive. And that implies, right, if additional units are less expensive, that we have economies of scale.